So, this is the first video in a series of videos about electricity and magnetism. Should be a lot of fun. Should be a lot of fun. It's going to cover a lot of different stuff. It's going to be like your second semester in your first year of physics. Just a little more tedious, but that's okay. We'll go through it together. And just to start off, I want to talk a little bit, kind of, I guess, motivating us on what we're doing. Kind of a little introduction before we start getting into the heavy stuff. So hopefully in the next video, we'll start doing a little bit of math review, which will be helpful in any physics you're looking into, really. But before we do that, let's kind of get a little introduction. So there's four kind of realms of physics, or realms of mechanics, I suppose. And they're right here. So the first one is classical mechanics. Right here, classical mechanics. That deals with 99% of stuff that you'll encounter. That's kind of the stuff we see every day. Planets, for example, right? Planets, bodies in motion, if you roll a ball down a ramp. In this case, electricity and magnetism is a form of classical mechanics. But basically, anything... 99% of what you'll run into, we can use classical mechanics. This is Newton. This is Maxwell. That's all these good stuff. Now, let's say things are going really, really fast. So this is the speed goes along here. So you're going really, really fast. Then you start dipping into relativity, which, if you're watching my series on an intro to modern physics, we're actually talking about special relativity, and we're wrapping up on it pretty soon. We're finishing up on the Lorentz transformations, and then we're going to get into a few other things, and then some dynamics, relative dynamics, and then we'll actually move on from there. So when you're dealing with something going comparable to the speed of light, you can't use mechanics. It doesn't give us the right answer. We have to use relativity. Likewise, when the size goes down, this is our speed, right? When the size gets really, really small, we're talking comparable to the size of protons and electrons, we have to use quantum mechanics, which we're not covering yet in the modern physics playlist, but we will get there. This will be covered in the video series, but we're doing relativity first. And sometimes you deal with something that's number one, very small, and number two, moving at relativistic speeds. And that's quantum field theory. Now, obviously, to understand this, you're going to want to understand classical mechanics and relativity and quantum mechanics. Then we can start talking about QFT, quantum field theory. But this is just a nice little chart to see, kind of what's going on here. So hopefully that makes sense. Here's a picture of an atom, even though it doesn't look like that. We'll talk about that later. Hopefully this kind of introduces you to the different branches. Now, the next thing I want to talk about is the four types of forces. So if we start at the bottom, the strongest force is, you guessed it, the strong force. And what that does is that basically holds together protons, electrons. It binds quarks together. And this is a pretty short range force, so you have to be pretty close to notice it. And it's very, very strong. It's all the way down here. That's our strongest force. Going a little weaker, we have electromagnetism. And that acts between electrically charged particles. And that is infinite. Now, it can start to fall off the further away you get away from the charge, but we'll talk more about that later. The other thing we have is the weak force, and that governs particle decay, so like radioactive decay. That's also short range. It's not something we experience in our everyday life. The next one is gravity, which acts between two objects with mass. Now this one's really weak, right? That's really, really weak. And that kind of like the charge is infinite. If you remember, force of gravity is big G, little m, big M over r squared. where G was 6.67 times, I think it was 10 to the negative 12th. I don't remember exactly, but something like that. It's a small number, so we're dealing with a very small force. In fact, it takes a huge mass. We're talking the mass the size of like a planet or a moon to really have a noticeable effect. Okay, so we talked a little bit about that. I also want to mention, you might ask, hey, okay, I've taken physics 1, physics 2. What about like friction, normal force? What about all these other forces we worked with, right? Those are actually an electromagnetic force. So a lot of the things that you would call, for example, friction, air resistance, which is a form of friction, that can be explained with electromagnetism. So they actually fall into that category. The next thing I want to talk about is how electricity and magnetism were separate. Now, originally when we were studying this, if we looked at electricity, okay, well that had to do with charges, right? We would have some positive charges, some negative charges, and positive would repel each other, and negative would repel each other. But positive, negative, or negative, positive, they would attract each other. That was kind of their own thing. Then what happened? Well, magnetism. Magnetism was also its own thing. What was that? That was like, magnets. If you look at a compass, these were kind of we thought there were two separate things. Well, a lot of smart people, and we usually give credit to Maxwell, unified these two, which we learned in our second semester of physics with Maxwell's equations. So it turns out electricity and magnetism are really all of the same thing. So magnetism is really just a product of moving charges. That's really all. They're essentially, well, obviously they're different, but they're the same branch. And Maxwell showed that, hey, if you have moving charges, that's really all we're working with there. The next thing I want to talk about real quick is fields. I guess we'll do this. Fields. And basically, let's say we have, well, I'll do plus, we'll say these are charges. So how do charges here let's say we have some other charges. I'll switch them up. How do they affect charges there? So how do these charges interact? Well, let's say you have a positive charge. We have an electric field that permeates out like this, and negative charges go the opposite direction. And the important thing to know is that these field arrows, they continue, really far away. They're also three-dimensional. So what's happening is, let's say these charges, how do these charges affect like this charge? Well, they emit this field that goes all through space. And what happens is when a charge that feels this field, that feels a field which are given off by these charges, experiences a force, and that force is equal to Q times our E field. We'll talk about that more later, but hopefully you remember that from your second semester physics. Okay, guys, one last thing, and that's I want to talk real quick about electric charges. Now, the first one is charges come in, so they come in positive and negative charges. And we talked about positive and positive, negative and negative. They repel. And negative, positive, negative, or positive, negative attract. Okay? Another thing is charge is conserved. Charge is conserved. So, basically meaning you can't create or destroy charge. It's conserved. In fact, the total universal charge, so our total charge in the whole universe, is fixed. It doesn't change. And the last thing is that charge comes in lumps. And what I mean by that is you could have a negative charge, you could have a positive charge, but they come in lumps of E, which is the charge of an electron. So maybe 1E, or 2E, or 3E, or negative 5E. What you won't get, so this is all good. What's bad would be something we don't have is like half E, or pi E, or 7.392E. That's not things we're going to get. We're only going to get it in lumps like this. So hopefully that makes sense. We're going to start talking about some math that'll be really helpful. In fact, that'll be a good chunk of that'll be a very good chunk of really the first half of this is just going to be reviewing math. And I think it'll be very important no matter what math you take. So the first half is almost like a math methods course. Not quite as in-depth, but it's going to cover a lot. So be on the lookout for that.